Hey everybody, so let's go ahead and build this spreadsheet. So you should be able to download this file, the initial file, and what we're going to do is fill out the formulas, and I've got the formulas all laid out as pictures on the right, and then in column B here I also have the formulas, so it should be pretty straightforward to fill this out. I've got green cells are where we're going to enter the data that changes, and then the gold cells, these are what we're going to calculate based on the values that are entered in green. So um, the inputs are the arrival rate lambda and the service rate mu. So let's say the arrival rate is 15 and the service rate is 20. So let's first talk about what this means. Let's assume these are per hour. It could apply per day, per month, whatever. But for the example we're going to do, it's per hour. So what we're saying here is 15 customers are going to arrive on average per hour. And what's the process capacity? We could handle 20 per hour. So first thing you want to look at is make sure that your arrival rate is not higher than your service rate, or you would never catch up. But here we go. We got 15 arriving per hour. We can process up to 20 per hour, and those are on average. So what are we going to calculate? Well, the first one first couple we're going to calculate are real straightforward. First of all, the average inter-arrival time is the multiplicative inverse of lambda. So 1 divided by lambda is, let me go ahead and do that in Excel, equals, cell C3 is where I have lambda. Oops, I forgot to do the 1 divided by. It's equals 1 divided by C3. And the inverse of mu is the service time, so that's equals 1 divided by cell C4. So what we're saying here is the time between customers arriving is 0.07 of an hour, and the service time, how long it takes to handle each customer, is 0.05 of an hour. Now, some of you may work on decimals of an hour, but I don't. I work in 60 minutes. So let's calculate quickly what these mean in English. So here in column D, I'm just going to add some calculations to figure out what this means in terms of minutes. So if I say take the inter-arrival time, cell C7 times 60, that means that every 4 minutes a customer is arriving. And as you can see, with an arrival rate of 15 per hour, yeah, that makes sense. Every 4 minutes, that leads to 15 per hour. And how long does it take to process each customer or complete each customer's transaction? Let's take 0.05 of an hour times 60 minutes per hour is 3. So it takes us 3 minutes to handle each customer. And as you can see, if we've got a capacity of 20 customers per hour, that makes sense that each customer would take 3 minutes. So these two here, I'm just expressing in minutes instead of hours. Is also it's the same thing, just different time scale. So the next thing we want to calculate here in gold is the system utilization. This is the Greek letter rho, and that consists of lambda divided by mu. So I'm going to say equals C3 divided by cell C4 is 0.75 or 75%. So what we're saying there is the person in this system is busy 75% of the time, 25% of the time they're free, available to do other things. And you can kind of look at the numbers and go, oh yeah, okay, that makes sense. If 15 arrive per hour and we can handle up to 20 per hour, that kind of makes sense. That 75% of the time the server is busy. The next couple formulas are just a little more complicated. The average number of people who are waiting in line is the lambda squared divided by the quantity mu times mu minus lambda. So let's go ahead and do that in Excel. First, we're going to do lambda squared, and then we're going to multiply by mu times parentheses mu minus lambda. So I've got the formula C3 squared times C4 times C4 minus C3. And that leads to the wrong answer. So what did I do there to get the wrong answer? Well, I typed multiply there when I should have typed divide. So the correct answer is 2.25. So sorry, here's the correct formula. It's the cell C3 squared divided by the sum C4 times C4 minus C3. So this means on average 2.25 people are waiting in line to get service from our one server here in Model 1. The average number of people in the system, this includes people being processed and people waiting in line, is lambda divided by the quantity mu minus lambda. That's a little easier. Hopefully I can get that this first time. Divided by this mu minus lambda. Whoops. And I'm getting 3.0. So on average, there are 3 people in the system either waiting in line or being processed. The next couple are pretty straightforward. Average waiting time, how long do people have to wait in line on average? Again, some people walk right up, get service right away. Some people have to wait a while. What's the average? Well, it's our LQ, which is our average number waiting in line, divided by the arrival rate, lambda. So that formula is equals this quantity in C10 that we already calculated, divided by our lambda in C3, and so that's 0.15 of an hour waiting in line. Average time waiting in the system. This is the average time being serviced plus waiting in line is the average number in the system, LS, divided by lambda. So that equals the number we just calculated, LS, average number in the system, divided by our arrival rate, lambda, is 0.2. So again, what I might want to do here, just to convert these to minutes, is in column D here, multiply each of them by 60. And why did I? Forgot to hold the shift key there. So what we're saying here is customers are arriving on average every 4 minutes. It takes on average 3 minutes to process them. The average time waiting in line, 9 minutes. And the average total time in the system between waiting and being processed, 12 minutes. So that's the first part of our calculations here. Interesting information, but what we also want to calculate here is our probability of having certain number of people in line. So let's look at column B here. What I want to calculate in B17 here is the probability that there are 0 people in line or in the system, so either in line or being processed. In B18, it would be the probability that there's 1 person in the system being processed. In cell B19, 2 people in the system, so 1 person being served, 1 person waiting in line. So the formula for that I wrote out here, and it's also in the right over here, is this formula here. So rather than me read it, let's go ahead and do it here. What we're saying here is the probability is the quantity 1 minus lambda C3 divided by mu C4. So that quantity times the quantity lambda divided by mu to the power of whatever number we're looking at here. So that's cell A17. So what we're saying here is the probability that there are 0 people in the system is 0.25 or 25%. Now, quick little sanity check. Let's go back to our calculation up here. The system utilization is 75%. So we already calculated that 75% of the time the system is being used, or there's customers in the system somehow. So if 75% of the time there's customers in the system, the probability that there's 0 customers in the system is 25%. So that makes sense, right? Now, what I want to do is take this formula and drag it down here. I did 0 to 9. You could do 0 to 1,000,000 if you wanted to, but we'll just do through 9. In order to drag the formula down, though, I want to do absolute reference anytime I refer to cell 3 or C3 and C4. So I'm going to add the $ with the F4 key. I'm going to leave the reference to A17 without $ because I want that to automatically update. That amount stayed the same, but by adding the $ now I can drag this formula down, and you can see my probability of 1 customer being in the system is 18.75%, 2 customers 14.06%, about 10.5% of 3 customers in the system. So now keep in mind this probability that there's 3 customers in the system, that would be 1 customer being processed, 2 standing in line, is 10.55%. That's the probability of exactly 3 customers in line. So what I want to do in column C here is say, well, what I'd really like to know here is what are the probability of less than or equal to 3. So the probability that there are less than or equal to 3 in the system is the probability that there's 3 plus the probability that there's 2 plus the probability that there's 1 plus the probability that there's 0. So so to calculate this cell right here, what is that, C20, I want to add up all of these probabilities and say that's my probability that it could be any of those 4 cases, either 0, 1, 2, or 3 in the system. So how do I do that? Well, what I'm going to do here is equals SUM from cell B, and this is, what am I in? I'm in cell C17. I'm going to say that that's the sum of B17 through B17. Now, hold with me. That seems like kind of a dumb thing to do. But if I put $ on the first B17, so I've got formula of equals sum of $B, $17, colon B17. If that is my formula, then I can drag that down, and you can see that it works out nicely, that my number here for 3 people in the system, it turns out there's a 68.36% chance that I'm going to have either 0, 1, 2, or 3 people in the system. So by adding the $ to the first B17 up there when I dragged the formula down, that stayed B17, and then the ending range of my sum function got updated to my current probability here. So again, I'll go back to that formula here to show you, and you just drag that down, and great. So then the other thing that's interesting, the last thing we want to calculate in this video, is the probability that you're going to have more than that number of people. So this is, so for example, let's go back to my probability of 3. Here we've got 68.36% chance of having less than or equal to 3 people in the system. What are the probability that I'm going to have more than 3 people in the system? So 4, 5, 6, 99, 2000, whatever. All those numbers, that probability is the additive inverse of 0.6836. So 1 minus that. So to calculate column D here, I just say equals 1 minus column C, and I can drag that down. So you can see here I've got a 25% chance of 0 people being in the system. I've got a 75% chance of more than 0 people being in the system. And again, let's compare that to our system utilization number. It's the same. We're doing good. So here, for the 3 people in the system, we have a 31.6, so roughly 32% chance of more than 3 people being in the system. So if we have some kind of concern, like, hey, we don't want too many people standing in line. If there's 4 people in the system, that's 3 people standing in line. If we have 9 people in the system, that's 8 people standing in line, and so on. So maybe what we want here is to try to keep this number of more than 3 people in the system, which is 2 people or more, or more than 2 people rather, standing in line. Maybe we want to, with this number 32% here, maybe that seems kind of large. So we'll do some playing around with that in the next video, but I wanted to end this video here to just say that what we did is we added the formulas to calculate these numbers here. We converted some of them to minutes instead of fractions of an hour, and then we calculated the probabilities down here. You've got all the formulas in column B here spelled out. So hopefully this makes sense, but if not, if you have any questions, let me know. Otherwise, you can go on to the next video.